In this video, we are going to learn 4 different arguments to justify this n-1 in the expression of the sample variance. Let's get familiar with the dataset in this video. So we have a population of 5 data points, x1 to x5, and x1 and x4 are our sample. Therefore, we have the population mean, population variance, population standard deviation, and the corresponding sample parts. Check the formula and values if you forget. Ready? Let's go. The first argument is my go-to argument if I want to explain this idea to someone who only has 30 seconds. If the sample size is 1, there's no way you can tell anything about the population variance. As variance is not well defined for a single data point, using n in the denominator leads to the wrong conclusion, as if we are treating the sample as a population. To fix this problem, we have to pick n-1 rather than n in the denominator. So we have 0 over 0, an expression that we usually don't want to see. But here, we actually love it because it properly represents the fact that we have no knowledge about the population variance. Let's move on to our second argument, the compensation argument. First, let's set our sample size to be 2 again. If we do know the population mean, mu, then the sample variance should look like this. However, this mu remains unknown to us during our calculation, so we have to estimate that. How did we estimate it? We use x bar, the average or the mean of all our samples. This is our best shot, but it comes with a big price. If we write the sample variance as a function of the population mean or its estimation, then it's a quadratic, opening upwards, which means it reaches a minimum somewhere. The green vertical line represents the population mean or its estimation, and this number represents the sample variance we calculated. It seems that using x bar to estimate the population mean, we automatically minimize our sample variance. This is cheating, and it clearly sounds biased, so we have to compensate for this bias by inflating the sample variance a little bit. And this concludes the compensation argument. In our third argument, we are going to look at it from the perspective of degrees of freedom. In the compensation argument, we treat the sample variance as a function of the unknown population mean. Look at this formula. It basically says that every sample point contributes to the variance, and then we distribute it evenly to n parts. If I know the mean of the population, I can write the sample variance as a function of my data points. If my samples happen to be x1, x4, I get a value 2.5. If my second sample point changes to x5, I get a new sample variance 4. Similarly, my first sample point can freely change to x3, so I get a new variance 2. Did you get it? If we know mu, each sample point can freely change. Each of them carries a piece of information that is independent of any others. However, if we don't know the population mean, we have to use x bar, the sample mean, to estimate it. This has a big problem because although it seems that the sample variance depends on 2 samples, but only one of them can change freely. Because if my xi change, my xj will be forced to change. This is what I mean. So let's say xi and xj can be continuous right now, and we already use their mean to estimate the population mean. X bar is a sample mean. So if I vary xi, my xj will change correspondingly. Therefore, it is only free with a degree of freedom 1. Practically speaking, the degree of freedom is the number of pieces of independent information that goes into the estimation process. If you have n sample points, by the time you estimate the population variance, a slice of the pizza is already gone. The last unbiased estimator argument is a classic mathematical statistics argument. Let's say we don't know the population mean and we still use 1 over n. If this formula is good, When I take the expectation, I should get the population variance. So let's expand it. The xi minus x bar squared can be expanded to 3 terms. There's no magic at all right now. It's simply a plus b squared. After expanding the expectation, we need 2 facts to continue. The first fact is that the sample points are independently and identically distributed. The second fact is that expectation is a linear operation. The IID assumption will allow us to treat each xi equally. The second fact allows us to move e in and out of the summation sign. Now our first term is basically the population variance summed n times then divided by n, so it's just the sigma squared. And our last term is the average of n copies of the variance of the sample mean. If you watched this video to this point, you probably know this formula. If you don't know, this has an intuitive meaning. The average of a few sample points has a smaller fluctuation. Simplifying the last term, we get sigma squared over n. Now let's deal with the middle one. Mu minus x bar has nothing to do with the running index of the summation. The summation of xi is just n times x bar, and the summation of mu is just n mu. So n cancels, and we can flip the sign. What's this? This is 2 times the variance of the sample mean. So it's negative 2 sigma squared over n. Everything boils down to n minus 1 over n sigma squared. It is not sigma squared. Therefore, our sample variance using n in the denominator always underestimate the population variance. The solution is of course using n minus 1 rather than n, so our estimation of the population variance is unbiased. As one last note, this formula is an unbiased estimator for sigma squared. But if you take the square root, it is no longer an unbiased estimator for sigma. Yeah, I love mathematics.